All right, so let's get started for the day. Welcome back to whatever class this is, 68410. Nice to see everybody, those of you who are brave enough to survive another week. Let's see, in terms of course announcements, before we get started with class for today, let's see, so some of your colleagues just reminded me that we do not have class on Tuesday. In case you're not cognizant of the weird MIT spring schedule situation, at least pre-COVID. I forget if they did last year, but essentially there's like a weird day in the semester when a Tuesday pretends to be a Monday, and that's next week. So the next time we will have lecture is next Thursday, which is great. I'm going to have an exciting Tuesday. Other than that, your homework is due, I guess, this coming Wednesday. How many of us have started? How many of us have cheated and looked at the solutions I accidentally uploaded? Right? I almost got you. Okay, that's great. So do get a start on that. This is a PhD level course. At the end of the day, the homeworks are intended to be challenging. Some of the calculations here are annoying, but turns out that's life in the city. In geometry, there's a lot of annoying calculations. So welcome to the club. But it's the kind of thing you can either be clever or you can just follow your nose and do lots of annoying. And either one of those will lead you to the same answer. You can choose your own adventure. Okay, any questions so far on the logistical side before we get started? Yes?
When is the weekly question answer?
Fridays, I believe. Yeah, there's a deadline in Canvas. We'll just respect whatever that is. Yeah. Oh, right. So as a reminder, this week is your first week for these little weekly engagement things. I saw some of you posted thoughtful questions on Piazza, which is fantastic. Hopefully others of you responded. I did not actually look, I'll be honest. You can do that. You can report on a thing that you have read. I suppose you could go to the Writing Center for your final project, but it might be a little early for that. Yeah, any of those. So take a look at the course website for detailed instructions. It is intended to not be a whole lot of effort, just something to keep you engaged in like fun geometry stuff. In terms of reading, by the way, a few of you asked, like, you do not need to choose a reading from that list of papers that I sent you. You can choose another one. However, it should not be a reading that's like, you know, my MEng advisor told me I should read a paper about, systems. Like, as long as it's geometry related, that's fine. And related to the contents of this week. So, like, we've been talking about curves, so curves show up in a lot of places. So you'll have no shortage of places to find suggestions. I believe in the document I uploaded, I included some like graphicsy stuff, some like time series style things, and some physics papers. Largely, those are just my own Googling. I'm sure you can find some yourself. Every year, I look at the things that the students add, and then I just add them onto that document. Any other logistical things? Okay, so today we continue our discussion of curves, and this is going to follow kind of a prototypical pattern that we'll do a lot, at least in the first third of this course, which is we'll kind of ping pong between smooth differential geometry and discrete. Obviously, in a class like that, what that means is that you get half the time to cover both. So meaning we're not going to hit every single big theorem in differential geometry, nor are we going to do every fancy discrete differential geometry construction you could think of. But really the idea here is to give you some intuition and feeling for what these fields are about and the kinds of calculations that we do so that you're equipped to go out and read all these things on your own. Okay? So today is going to be our first example of that. In our last lecture, we talked all about smooth curves, right? And in particular, we derived an object that is going to come up many times today called the Frenet frame. And the Frenet frame is nothing more than this moving pair of vectors in the plane, or triplet of vectors in 3D, that give, in some sense, things that are parallel to the different derivatives of your curve along the curve itself, right? So there's the tangent vector, which is parallel to the curve. If we differentiate the tangent once, we showed that you get something perpendicular to the tangent, which we call the normal. And then if you do it again, or if you take the cross product of those, you get a third guy called the binormal, right? And so these things form what we call a moving frame that moves across the surface. And once again, MIT's Wi-Fi is disrupting my laptop. Okay. Along the way, one thing that we did is we said, well, if we want to make measurements about a curve, Jesus, now it's buzzing, it's the whole thing. If I want to make measurements about a curve, and I only know how to like walk along the curve in space, then I end up having to do kind of an interesting thing, which is to keep taking my measurements and projecting them back onto like the Frenet frame, because that's my only sort of frame for what it means to do geometry on this object. And in particular, in 2D, we derived one number called the curvature, remember this was derivative of the angle here, which describes the bendiness of the curve. And our story was that basically, if you know the curvature function, you actually know the geometry of the curve, and obviously the other way around, yeah? And so this is a great example in differential geometry of what we try to do. We say, okay, there's some measurement we can make about a shape. Remember, defining that word measurement was a little tricky. We have to make sure it's invariant to parametrization. But once we do that, the next question we want to ask is are there other interesting or meaningful measurements locally? And in this case, the answer is no, right? Like, curvature is everything I need to know about a differential curve, at least nearby. Cool? Nods, acknowledgements, like those of you on your laptop, look up, eye contact. Cool. All right. So, good. I made one person nervous. I've done my job. Beyond that, we can derive other quantities as well. So one thing that we did, in addition to looking at a local quantity about a piece of geometry, right, like the curvature, we also derived a second thing called the winding number, which is, you can think of it like a global way of describing a shape. The more grown-up thing to say is that this is a topological invariant. And in fact, it is an invariant in the sense that if I take a curve and I kind of smush it around in a smooth fashion so it's never allowed to develop a kink, right, that's a big gotcha, then this thing remains constant, even though, notice that it's like the integral of something differential looking, right? Which is kind of cool. Like, you could get this constant integer value out of what looks like a calculus kind of style math, right? And that's not obvious why these sorts of things should happen, right? We're on 3D surfaces, the story's going to get even more complicated than that, but we're going to have an analogous theory that tells us, for example, if we integrate a quantity called the Gaussian curvature, we get something related to Euler characteristic, right? That'll be our sort of big fact in that universe. But we're not there yet. So we first did the 2D case. Winding numbers don't make sense in 3D because you kind of need a point to wind around, right? You need orientation. But in 3D, we also derived an object called the moving Frenet frame, once again, or Frenet array, or I think sometimes there's a third name attached, which I've honestly forgotten. But in any event, once again, the story is very similar, right? I have this moving set of 3 vectors that's like sliding along a curve. One of them is the tangent. The normal has to do with the first derivative of the tangent or the second derivative of the curve. And that kind of, you can think of the normal direction as kind of like the steering wheel change. And then you've got this binormal direction, which is kind of like the lift out of the plane, right? And because we have this new direction, we need to describe the rates of change in all of these things. And so we had to introduce a third value, torsion, which is, again, sort of quantifying out-of-plane motion, right? Like one thing you can and should check at home, which is a byproduct of this formula we have here, be a good homework problem, would be if you have 0 torsion, that this is actually a plane curve, that like even though you're in 3D, right? Is that obvious from this formula? Yes, because then the derivative of the binormal is 0, right? Cool. Any questions about our little review so far? Yes?
Can you explain the diagram and what the rotation for the tau and the kappa are in terms of the other things? I was staring at it last class and like,
Oh, this little picture?
it seemed like they're around.
Oh, it's funny. I borrowed this from Wikipedia. Let me think about it for a second. Sure. Yeah. So essentially, so we have this curve here, right? And then you've got this car that's driving along the curve with unit speed. And essentially, the car has these little 3 vectors pointing out of it, right? There's the tangent vector, the binormal, which is like the normal, which is like kind of to your left, the binormal, which is kind of up. And so as you're driving your car along, all 3 of these things are changing. And what this picture is trying to communicate is like you can kind of look at the change of these 3 axes, and they rotate about 2 different things, right? They rotate about the binormal and the, I guess, the tangent here. And if you look at the rates of change of these different things, then you'll notice that one of them is curvature and one's torsion. So for example, let's say the torsion is 0, then the binormal is not rotating, which corresponds to the planar case. It's exactly what you'd think. And similarly, if torsion is 0 and curvature is not, notice that you're rotating about the binormal, meaning you're staying in the plane of the curve and your heading is kind of changing. So that's, yeah, this picture is a little bit mysterious. That's a reasonable question. Any other ones? I should remove that and put something less cryptic. It's mostly just there because white space stresses me out, and whatever. Okay. By the way, the picture on the right should also trouble you the tiniest bit. I said that these things have to do with curves as measurements, but really they have to do with oriented curves. As a detail I keep eliding a little bit, because otherwise notice that this entire Frenet frame, if I drove my car in the other direction, would flip upside down. Yeah. So for a lot of the measurements we'll make, like curvature and torsion, that actually won't matter, but it is just worth noting that there is this like chirality that we often don't think carefully about. The reason we don't think carefully about it is like when we do the 3D case, we often talk just about intrinsic geometry, like measurements that you make without knowing that there's space around your geometry. And there, these kinds of matters might not matter quite as much, because it's kind of hard to have some notions. Like certain things you just need an oriented manifold or they don't make sense. Other ones, it just is irrelevant. But we'll come back to that later. Okay, so today, I mean, at the end of the day, we are in course 6. We're not in course math. And so because of that, it's not enough to just do a bunch of like fun things, prove a theorem, saying that they're enough, and then like, you know, clean our hands and move on to the next topic. Really, the question that we're trying to answer here are what does it mean to do exactly the same calculations we've already done, but in software, right? And it's going to turn out that it's not so obvious how to do this stuff. And moreover, there's a lot of engineering decisions that feel kind of innocent, but actually lead to vastly different discretizations of these values and different behavior for your geometry software. Now, obviously, I mean, I'm overstating this a little bit. Like for curves, everything is pretty mild and well behaved, but these are good examples of like themes that are going to come up as we consider higher dimensional and more complicated calculations, right? So this is all, like, essentially this entire week of this class is sort of a warm-up for everything else that we're doing, because it's a little microcosm for all the different problems that come up when you try to take a smooth theory like differential geometry and make it work on like a fundamentally discrete computational object, right? That's sort of our point here, which I think I've managed to repeat about 600 times. Okay, so if you took my undergrad graphics class, or any graphics class, or computer-aided design class, or whatever, probably this little figure might look familiar to you. And this is sort of the standard way that a lot of people talk about curves when you talk about computational stuff. So this is a picture of a spline. It's got control points. And typically, in like kind of old school modeling, when you do curves and surfaces, you view these things as maybe parametric functions of t. You choose your favorite class of functions, and then you kind of work in those. So a very typical thing to do would be to think of the set of cubic functions. Remember, we actually derived a few lectures ago that that's sort of a reasonable set of interpolants because of points and tangents. And that would derive the set of Bezier curves. And then, like, if it has some more complicated shape, like an S or whatever, a lengthy thing, it's obviously no longer enough to just have one of these segments. We have to start gluing them together, right? So in this class, the class is titled Shape Analysis. We're trying to say, like, if we have an input is a shape, like in this case a curve, and I want to derive something about it, like its curvature, which maybe is useful as a feature for a learning system or whatever, right? Then the question is, like, how easy is it to do the sorts of calculations that we derived in the previous lecture on this object? And, you know, essentially cubic Bezier curves, they look innocent enough. I mean, they look just like little rainbows. That's nice. But the reality here is that they're actually quite complicated. So for example, I challenge you on your scrap paper to take the formula for a cubic Bezier curve and compute its arc length. Right? This is sort of the simplest possible thing that you could do for a cubic curve. This is the standard representation of a shape in like Adobe Illustrator. Yeah, and if I want to know how long that curve is, it's actually, to my knowledge, actually there's no closed form formula for this. If you just write out this weird integral, there's square roots, there's squares, and you'll find that there's actually no formula for the length of this thing. Yeah? So what does that mean? That means kind of necessarily when we're analyzing a shape as simple as a cubic Bezier curve, we're making approximations, right? Like, so probably if I asked all of you guys to do this at home, what would you do? You'd like take the curve, sample a bunch of t's, you know, fill in a bunch of line segments, and then, you know, profit. Use the lengths of those line segments as a approximation of the length of the curve. Notice, by the way, that's usually an underestimate of length, right? Because we're replacing curved segments with straight lines. Yeah. So in general, this is sort of illustrative of a simple fact. So, oh, incidentally, one thing you can do is compute curvature of this object. I didn't put it on your homework because that would be really nasty of me. It's just like some big ugly formula that's like not nice to look at. But the reality is that there are very few closed form expressions for these really tidy measurements that we talk about in differential geometry. Even just like arc length, which is about the simplest one. We'll see that basically everything we do on surfaces is just built on the definition of arc length. And so they're rarely closed form expressions. And moreover, if you are so lucky as to find a formula, like for instance, for the formula for curvature and torsion of like a cubic Bezier curve, it's not nice. And moreover, there are a lot of subtleties that arise. So for example, let's say I want to compute the curvature of a cubic Bezier curve, right? That's perfectly fine, right? Like, I've got this nice smooth curve arc. But like we talked about, like, let's say I have a font, right? So on your computer, fonts are usually a bunch of cubic curves that are joined together, and we kind of join them in a way that makes their tangents agree. Now, to the naked eye, those curves probably, they feel innocent enough, like they look like smooth curves, but more often than not, what do you think the curvature is right at that point where they join? Infinity, right? It's really hard, given two curved segments, to figure out the condition that makes the curvature of those two objects agree at a given point. Making their tangent agree is not enough, right? Because this is some second derivative thing. And moreover, it's not second derivative with respect to t, it's with respect to arc length. So there's like all kinds of details there, which is why like your modeling software just doesn't bother, right? Like, and this can be a problem. So it turns out that your eye tends to be sensitive to visual differences up to about second derivative, like you can kind of see it. And so like people that design sides of cars and things are very sensitive to these kinds of joinery problems, and making things join with continuous curvature is actually just like an annoying computational problem in that domain. This is not obvious. It's even worse for surfaces. Okay, so here's going to be the philosophy we'll do for now. This is obviously a little bit flippant, but in some sense, the set of like piecewise cubic Bezier curves is itself not the set of all possible curves, right? There's a lot of curves out there in the universe. So in some sense, we're going to throw up our hands and say like, okay, well, we're only using approximations anyway. So maybe the right kind of basic representation for a curve when we're doing discrete geometry for the analytical setting would be just a bunch of line segments. We're just going to call that our analogy of a curve, because things like cubic Bezier, they look nice, so for like visual applications can be really important, but from an analytical perspective, it's not like we actually gained a whole lot. We end up making these kinds of approximation anyway. So here we're going to kind of figure out how much differential geometry, like basically how much of the previous lecture can we do if we're going to replace things like this purple curve with just collections of little line segments. Like, does it make sense to talk about curvature in this case, or torsion, or what have you, right? Now, that feels innocent enough, and for instance, arc length is perfectly fine, right? Like, what's the arc length of this? Probably just the sum of the lengths of the intervals. Notice now I've not made any mistakes, so we're good so far. But other calculations are going to be less easy to do. So for example, let's say I went back to my formula for curvature from the previous lecture, right? So curvature is the derivative of the tangent. So what's happening here? Well, this curve has got a bunch of straight lines on it. So along the straight lines, the derivative of the tangent is 0. That's right. And at all of these points, the tangent has a discontinuity. So the derivative of the tangent is infinity. So is this like a very exciting curvature measurement? I would say, probably not, right? So rather than doing curvature by just taking our formulas and trying to apply them directly to these objects, we're going to need to derive formulas that are somehow analogous to the computations we did before, but make sense on this discrete structure. Does that sort of make sense? What we're going to see is that this is an engineering problem. That like there are going to be a lot of different formulas that all kind of feel like curvature and have properties in common with curvature, but they're all not the same. And that's really frustrating. And kind of just life in the city in this particular research discipline, that like there will be one canonical smooth object and a lot of different ways to discretize it, and there's no correct and incorrect choice there. They're just different, right? And it's actually kind of an interesting theoretical question, like why is that? That like, why is it so, like why can't we all get along, And somehow it's built into the mathematics of this stuff. Now, if you walked over to my friends in numerical analysis, they would have a very different approach, right? They'd say like, okay, so for example, the curvature is derivative of the unit tangent. Maybe I like locally fit a little curve to like adjacent sets of 3 points, and then I take the curvature of that curve as like an approximation of the curvature of the smooth object that I'm sampling from, or something like that, right? And so this would be the sort of discretized perspective, right? Where like I'm trying to prove some limit, like as the sampling of my curve becomes more and more dense, this measurement that I've made approaches the curvature of the smooth object. Yeah? But that's sort of not the regime that we're in. We're dealing with a regime where I give you a bunch of points on a discrete object, and I don't give you the option of sampling more. That's all you got. And so in that case, this theory is sort of relevant, right? It kind of says something about the approximation quality, but it's also like somehow maybe not quite the right thing that we're trying to capture in some of the measurements we're making. Now, in the curve case, what we're going to see is that they end up being kind of the same. Like, it's sort of okay. But like, basically the point that the reality check that I want you to have is that in a lot of applications, like h is just some positive number. I have no resolution in my data beyond some canonical scale. And the question is sort of, should I do my measurements and think about them in a different fashion when that's the case? Yeah, so this is a philosophical thing, sort of. Now, in an ideal world, we try to do both, right? Like, we're going to want some curvature computation, for example, that maybe makes sense on a discrete curve and also approaches the smooth one as I sample it. And that is possible. We'll see that the ones that we compute today actually do have that property. Yeah, so that's the basic setting that we're in. So to put it differently, essentially there are two different considerations when we propose these different measurements. One of them is convergence to the continuous theory, and one of them is discrete behavior. So as an initial example of that, let's think about that winding number. Remember the winding number? It said that if I take curvature and I integrate curvature around the boundary of a curve, then I get a topological invariant, right? It just like tells you how many times the curve loops around itself. Notice that makes perfect sense for discrete curves too. What happens if I use like a divided differences style formula and compute curvature and then like some kind of quadrature style approximation for integrating? Am I likely to get the winding number of a curve? No, I'm likely to get a number that looks like the winding number of the curve. Is like maybe, if the winding number is 3, maybe I get like 3.01. And when I add some more samples, I get 3.0001, something like that, 2.999. But like, there's no guarantee that like that topological invariant is preserved when I move into this case, because I've made a bunch of approximations, right? Like, I don't actually know the smooth curve underneath my samples. Does that make sense? And that's perfectly fine, right? So the smooth theory, like the convergence theory would say that's great, as long as I have the property that as I add more samples, my computed winding number approaches the one that I want. But for some applications, that's not fantastic. So like if I'm using the winding number because I want to understand the topology of my curve, well, I just got like a weird fractional number, and I don't really know like how many times does my curve loop around itself. It's not obvious, yeah? Now we're all engineers. We could do a reasonable thing like round, and you'd probably be fine. But there's just that little uncertainty sitting in the back of your head. And of course, numerical analysis professors like myself are very good at cooking up little boundary cases where those like innocent little rounding steps go very far wrong. I'll let you cook up one on your scrap paper. The hint would be to add like a really sharp but little tiny kink on your curve. Okay, so one thing we might do is we might say, okay, for curvature, maybe I'm going to try and come up with some approximation of curvature that is self-satisfies some winding number theory of itself, that itself satisfies a winding number formula before taking that limit. So in other words, because the winding number of a polygon makes perfect sense, right, just like in its own right, maybe I can use that to engineer a notion of curvature that preserves that theory exactly before I take a limit. We're going to see exactly that in just a minute. Okay? So in other words, we're going to do this really bizarre thing, which sounds like a mathematical contradiction in terms. We're going to be examining different discrete theories of differentiable curves. And basically the punchline, sorry, I'm going to, like spoiler alert here, we're going to take two different notions of curvature. One of them is like trying to preserve the winding number. The other one's going to be from your homework, that you get curvature as the derivative of arc length. And we'll see that those lead to two different discrete curvatures. Like they're not the same. And so this is going to be our first example of like a no free lunch kind of scenario here. Okay. And really that's just to like the plural here is quite critical. Okay. So let's dive into a little bit more detail here. If you recall this little picture from our previous lecture, we've got this framed curve notion, and if we're working in the plane, then curvature is a lot easier to reason about because we have this angle theta, which is telling us sort of the heading of our curve. And so you can think of the tangent as really the cosine and sine of some angle theta. That also made it very easy to derive that winding number formula because, of course, it's like basically exactly just the tangent theta as I loop around this thing. Yeah? This story familiar? We remember this? I appreciate this little corner here because they nod. I'm going to be looking at you a lot. That's great. So in particular, we define this thing, by the way, I confuse turning and winding number. I think there's some books that these are two distinct terms, but the good news in today's lecture is they'll be the same. I guess turning number is like a purely 2D thing. In any event, we define this quantity, which is just the integral of curvature around our curve. And we can think of that as the change in theta, right, which is like the number of times the curve loops around itself. This picture familiar? Yeah. Cool. So here's the thing. If I have a curve which is now a polygon, this picture still makes pretty good sense. So remember that in particular, one way to understand this object is to think about the Gauss map, which is the map from our curve actually into its normal, so like rotated 90 degrees from the picture I have here. That doesn't matter a whole lot in 2D. And that like, as I walk around the curve, I'm really walking around a circle, and it's just the number of times that I loop around that circle. I can do pretty much exactly the same thing if I walk around an oriented polygon, right? So let's say I give you an oriented polygon, which just means a chain of points, right? Well now, between every line segment, I can figure out just the angle between those line segments, and that gives me a notion of turning angle concentrated at that vertex. Does that make sense? So like my Gauss map sort of discretely is this weird object now, right? Like I'm like standing at a point on the unit circle all along this edge here, and then I encounter a vertex and like I pivot a little bit, and then I like sit there again and I keep waiting, right? So that's what my Gauss map looks like, yeah? Now this object, you know, or a different way you might think about it is like maybe, you know, I've got an edge here, and I put this little tiny like curvy join right there, right? I'm kind of thinking of there being some limit of that procedure. This object itself has a y number, right? Just like how many times it loops around the circle here. Where we're now thinking of the edges as sort of points on this thing, and the vertices of the input domain becoming the arcs on the discrete Gauss map. By the way, in terms of just like calling out themes that will come up a lot in this class, notice that there's a duality here. Vertices here become arcs there, and arcs here become vertices there. Yeah. Later on, if we get to discrete exterior calculus in this class, about 50% of the time I manage to get to that topic, precisely the same thing is going to happen on a triangle mesh. Okay, so now we can define curvature. Does anybody have an idea? Actually, before I flip the slide, like how might you think about defining curvature of this object, like at a vertex? Yeah.
Well, you've kind of already given us an idea, sort of at the corner, the angle between like the first normal of the first edge and the normal of the second edge.
That's a fantastic idea. I like this idea. Let's think about this some more. So, I think, what do they say? You're in the right church, wrong pew here. But you've answered the right way that I suggested because it's almost right, but we're going to have to consider a boundary case here. Thank you for walking into my trap. I appreciate it. So, let's say that I approximate a circular object, like this one. By the way, I'm giving you a hard time, but you're the only guy that raised his hand, so you're doing better than everybody else here. Okay. I take my, my domain, and I can discretize it like two different ways. Maybe the first time I'm really lazy, and I have just 3 points, like that. So the curvature, by our definition so far, would be like, you know, the angle between this normal vector and that one, so like this arc here. So a pretty big curvature, yeah? Now, what do you think I'm going to do? Like, let's say that I made a new discretization of this thing with a bunch of little points, with like little line segments connecting each one of them. Ah, so close. Well now, what is the curvature at the same vertex? Well now I've got two normals that point basically up. So somehow does this measurement feel like curvature in the same sense as the previous lecture? No, because it somehow depends on the sampling of our curve. What was that? You could try it, yeah, you could think about some interpolation, right? Like you start discretizing, like basically filling in a little curve between these points. And certainly in the 90s, that's what we would do. But from the discrete perspective, we have this thing that we feel is related to curvature, but it's not quite curvature in the sense that like it obviously changes as we scale these objects up and down, right? Yes?
I think the problem is you're only using first order information, right? You sample those 2 points and draw lines between them, that's kind of like using the derivative, not using any higher order information within curvature second order.
Sure, so that's true. Like curvature is somewhat second derivative, and maybe it's not obvious how we use that here. I would argue that that's not entirely obvious in the sense that you have, like we view these lines as sort of the first derivative because it's sort of like there's a tangent here. Then you have some change.
Segments, right? The 2 neighboring segments, that's like a first difference. Versus if you include more segments, you'll get more.
That's true. Like we could include a larger neighborhood.
The more you use, you're going to start to get a real curvature measure.
That's true. On the other hand, I would think of curvature as a thing that I should be able to do at a point, right? Because like somehow in differential geometry, I don't need a big neighborhood to compute it, right?
Yeah.
I'm just arguing with you guys because that's my job. Yes, back there.
Can we just like fit circles like 3 points at a time?
We could, yeah, we could fit circles to 3 points at a time. I believe that will actually lead to a very similar measurement to the one that we'll propose. I actually don't know. That's a good question. But it's an interesting idea, and actually I do think that that would have the right property, that obviously as you scale your sampling, then the circles kind of tighten the right way. I have to think about that. I don't know. Any other ideas? Yes?
Should the lengths of the adjacent line segments matter?
Aha! Aha! We're onto something. Like, remember, the curvature has to do with d tangent ds. We've got a d tangent here. We have not accounted for ds. That is going to be our key intuition of what piece is missing. So let's dive a little bit farther, and I'm going to give you some more clues. I did see one more hand. Was there a question or another idea? Yeah.
This idea, what if we look at how sharply things turn almost? So if we extend the first line, and then we look at the angle between the first polygon and the second one, and then use that angle somehow.
Mm-hmm. So I think that's what our colleague has proposed, right? It's just the turning angle between adjacent segments. So it's like almost there, but we're missing a factor. Yeah. Okay, so let me give you yet another clue. And this is going to be almost there in terms of what we're missing in our measurement. In particular, here's a theory that in principle you all saw in 9th grade geometry class. Let's see if you remember this one. This is called the turning number theorem for polygons, or sometimes it has different names. You remember this picture? You probably did it with like a protractor and a compass and a straight edge. So in case you didn't, if I have a polygon, so this is a loop that doesn't loop on itself, right? So we're not going to deal with like the loop-de-loop case, although it's not that much harder. I can compute what they call in high school geometry class exterior angles, right? Which means, to go back to our idea back here, we take every edge, we extend it a little bit, and then we compute the angle into the next one. Yeah? Notice that that's the same as this angle here. It's just this picture is kind of flipped 90 degrees from that one. And one thing that you proved, you've probably forgotten by now, but you proved in high school geometry class, is for any polygon, if you take all the exterior angles and you add them up, you get 2 pi. Now, your high school geometry teacher probably proved this with high school geometry methods, induction and whatever. But what they failed to mention is that this is exciting because it's a topological invariant, right? There are a lot of polygons out there, and you do this little local calculation, like these angles, and somehow they all have to add up to a constant. That's like shocking, exciting, right? I mean, that's so cool. But notice that somehow feels very similar to the winding number theorem. That's because it's the same. This is another version of winding number theorem. So this is yet another clue as to somehow we're onto something. This number, this turning angle here, has something to do with curvature. And in particular, if we look at this formula here, what is it kind of suggesting? It's kind of suggesting that the sum of all the angles here, the sum of theta i's, kind of looks, if I took the limit, like the integral of curvature ds. Does that make sense? So to go back to Kartik's idea from earlier, notice there's a ds there, right? But there's no ds on the left-hand side. So somehow this number is the product of 2 things, kind of like the kappa and the ds. Yeah? So in fact, I think the sort of schematic picture that we often have in mind, if we want to relate these 2 notions, looks something like this. So we're going to take the dual to a vertex, where you kind of take the midpoint of the previous segment up to that vertex to the midpoint of the next one. And you're going to think of this theta number not as curvature, we're very close, but as the integral of curvature over this entire segment. Does that make sense? This is our first example of a thing that we're going to deal with in differential geometry a lot on the discrete side, which is called an integrated quantity. We don't have access to curvature, but we do have access to its integral over some Voronoi cell. When I say Voronoi cell, do you get what I mean? This is the set of points on this curve which are closest to this vertex than to any other. Okay? So if I wanted a pointwise estimate of curvature, I could get it, but now we're going to discretize rather than be discrete. In particular, I probably divide by the length of that little region. And notice that resolves our little contradiction, right? As we sample more finely, the theta gets smaller because the turning angles shrink, but the denominator also gets smaller because the size of the Voronoi cell has shrunken. Yeah? This story make sense? Cool. This is our first example of like a discrete quantity. And moreover, what we're going to see is there's a tiny, tiny amount of conserved structure here. Okay? Zoe, you look puzzled. What can I do to help you out?
Well, so you're defining it so that the Warner region is like all the points that closest to that vertex.
Mm-hmm.
But is that necessarily, or is that always like just you splitting the edges in half?
Yep.
Okay.
Good. Homework left to the reader on that one. Yeah. Fantastic. Any other questions? If you go into the theory of optimal transport, you could bias that using something called a power diagram, but that will be in lecture like 17 of this class. Cool. All right, so now we can start to resolve some measurements that felt a little contradictory before, but now make more sense. So for example, let's say that I have a sharp angle, like the one that I've shown you here. Notice that obviously the turning angle at this vertex here is the same in both of these pictures, which is, but like the curvature is not, right? And I feel like that's actually the right way to understand this picture in the following kind of schematic way, that here, if I kind of think of there being like a little smooth segment between these points, I would probably think of it kind of like this arc, this purple guy. But obviously, as I add more points, that purple guy is kind of getting narrowly shoved farther and farther into the corner. I have like a clue that there's more straight edge here than I thought before. This is obviously a schematic picture. It's just a way to kind of think about why this quantity might be a reasonable one. Yeah? But the high level point here is that we have an integrated value, the change in curvature, which actually happens to be the turning angle here, and it happens to be integrated over this dual cell. And when I use the phrase dual cell, I mean like everything closer to this vertex than anything else. Okay? All right. So now, like presto changeo, I can prove our discrete winding number, turning number theorem quite easily. And the proof is on the slide here. I don't think we need to write it down, which is the following. This is obviously kind of tautological. This is coming from the definition, really. Let's say that I want to compute the integral of curvature over my discrete curve in some reasonable fashion. Obviously, I can take an integral and I can break it into pieces, right? So I'm going to break my integral into one piece per Voronoi cell here. Let's see, I put these cute little parentheses. This is very hard to do in PowerPoint, so you should appreciate it. Okay, so obviously the total curvature of this object is the sum of the curvatures of each of these little segments here. Now we don't know the pointwise curvature, but we don't need it because we have the integral of the pointwise curvature in this region anyway. That's just theta I. And now I get to apply my discrete theory, which tells me that that's just 2 pi, or 2 pi k more generally if your curve cycles. Right? So what is this saying? This is saying if I take the discrete integral of the discrete curvature, I still get the winding number without, notice, like a squiggly equals sign, right? There are like plenty of other curvature formulas, including some later in this class, that will cover that do not have this property. So for example, it turns out another notion of curvature we'll cover in a second. Rather than having theta, you'll have sine of theta. Notice that those agree for small thetas. So actually, as you take the limit, they're the same. And in that case, this formula is false. It's approximately true, but it's false. Yeah?
This is sort of like an integrated motion of curvature along these line segments.
Uh-huh.
It's never useful to talk about, like, are there applications where the differential quantity is actually useful, or you want to talk about, like, the Dirac at the vertex?
It's a good question. So I would argue the Dirac at the vertex is precisely this quantity. There's a different universe where you say like, well, I actually really do think of this as an approximation of a smooth object, and like really I should like fit a curve locally and use the curvature of that thing. Yeah, like for instance, if you have like very coarse sampling and you're just interpolating or something. I think all of these formulas are sort of equally bad in the discrete case because you are filling in information that's just not there, right? But there are also some applications in between. So for instance, in subdivision, you do have the option of adding degrees of freedom to your object. And in that case, you really do care about this sort of limiting quantity. But maybe you use this as a proxy, and then you kind of have the option of like sampling more points, and things get a little more complicated. If that meant nothing to you, that's okay. Any other questions? Okay, cool. So here's a exercise left to the reader, and I really mean that because it's on your homework. So clearly, you guys have already all derived it. So in class last time, we derived the curvature-weighted normal of a plane curve by thinking about it as just the derivative of the tangent, right? But there's a very different way that you can get to the same object, which is you take the first variation of arc length. So in other words, like, how many of you have heard of gradient descent? Oh, fantastic. There's one or two in the back that don't, and I'm suspicious if we just have an attitude about raising our hand or if there's a question. But one thing you can do, just the same as like gradient descent to optimize a number or a point, we can do gradient descent to like optimize the shape of a curve using the kind of stuff that we derived last week, right? Like this little field along the curve saying like move these points in this direction to decrease arc length the most, right? That's sort of what, I guess, minus the gradient is telling me. And what you're going to derive on your homework, whether you like it or not, is the following formula, that if I take the first variation of arc length, so in other words, I have a curve, and now for every point along the curve, I'm going to compute a little vector saying if I kind of nudge my curve in this direction, it'll decrease the arc length the most. What I'm going to get is the curvature normal. And so this is another way to motivate curvature. It's sort of like, you know, the amount that you can decrease arc length locally. Notice that makes sense, because what is the curvature of a straight line? Yeah, you know, the answer to almost every question I ask in this class is the same. This is 0, yeah? So what is the curvature of a straight line? 0. Thank you, everybody. So notice that makes perfect sense in this formula, right? Because like, how do you make a straight line straighter? You should ask my parents. The answer is you can't, right? It's just straight. Okay, so right, so that would suggest a very different notion of curvature here, where maybe it turns out what we're going to do is you can do exactly the same thing on a discrete curve. Namely, let's say that I have a sequence of points xi. Right, so I'm thinking of my curve now as like literally just a bunch of samples from I equals 1 to whatever, smiley face. And now I want to compute the arc length of this object. Right, what could I do? Well, I could say maybe my arc length is precisely the sum over I of the distance from xi to like xi plus 1. I do not know if this notation agrees with your homework, so don't copy verbatim. Okay, I think we would all agree that this is the arc length, right? Then, like, what could I do? Well, I could come up with an analogy to this formula by saying, aha, well, I can sort of compute the gradient of L in the xi direction, right? So in other words, like, if I have this line segment here, how should I move this point to increase or decrease the length of this curve the most? Right? Obviously, I'll get a vector kind of like that for decrease. And the formula you're going to derive on your homework, because your instructor is mean and knows that it's an annoying calculation, is the following. It's actually a great application of high school geometry, so if you've forgotten all this stuff, you're going to have to go back and relearn it. Sorry. Is that the gradient of arc length with respect to one of these vertices is going to look like the normal to this object, where we define normal in a very careful fashion, scaled by sine of this turning angle divided by 2, with a 2 on the outside. This is just a formula. This is what happens when you take the gradient. Yeah? So in other words, this, again, maybe thought of as kind of integrated in this dual cell, is somehow our notion of the curvature normal of this thing if our starting point was this first variation formula, right? So we had two different starting points. One was this winding number formula. The other was this first variation. And they both end up like leading to the same quantity in the smooth case, curvature. But notice here we have a sine of theta, and in our previous formula we just had theta. Yeah? So like, for example, if I took this thing, I called this thing curvature, and I summed it over all the vertices, would I get 2 pi times the winding number? No, I get 2 pi times something that's kind of like the winding number. And that's where these things differ. Yeah? However, to talk about the difference between discrete and discretized, notice that as I sample more and more finely, so these curves become more and more smooth, right? The winding numbers go to 0, like we talked about at these, or the turning numbers rather. And notice that now these two quantities become basically the same if you just take the first term in Taylor series. Yeah? So this is a great example where you have two different approximations of curvature. And from the perspective of convergence, they're the same. From perspective of discrete behavior, they're quite different. Yes? That's a good question. I believe on the homework we do it in a lazy fashion, which is the normal is the direction of the first variation. No, but I think by symmetry it ends up being like the average of these two segments flips 90 degrees or something like that. Yeah. Notice you can prove a formula by this by just saying like n is the unit vector that you got by taking this gradient and dividing it by its norm, and then you have to work out the other term. But that's a very lazy thing to do. I would never. Okay. Right, so In other words, we have our very first example of a no free lunch theorem. I can either have a discrete turning angle theorem, or I can have a discrete first variation formula, but I can't have them both, right? Because they're necessarily contradictory. They lead to two different notions of discrete curvature. And that's what's so interesting and cool and frustrating about this research area, that like differential geometry is hard enough. Now I have like 10 different copies of differential geometry and they don't agree, and that's like mathematically correct. Like that's just what should happen. Yeah, there's nothing, we haven't made it like, it's not like 10 different like, physicists approximate curvature this way and artists approximate it that way. It's like, these are totally reasonable mathematical objects. Yeah. Right. Notice that one question we have not answered here is, do these discrete notions of curvature actually converge in the limit? And I will let you check at home if you really want to. It's like some divided difference style argument you can make that would check this kind of thing. And it's no fun because there's like a denominator there. It's just an annoying calculation. Yeah. Okay. And in fact, there are a lot of questions you could ask, right? You could talk about like, what is the rate of convergence, right? Like how many samples do I need to get a good smooth curvature approximation? Like what does your sampling need to look like? Does it need to be isotropic along the curve? Do I need more samples and bendy parts, that kind of thing? These are all totally reasonable numerical analysis style questions. Or to go back to our 10th question, which he asked in class, didn't like my answer and then put on Piazza, like what level of differentiability do I need to make any of these formulas work? So it's a completely reasonable thing to ask. Notice I'm only allowed to tease my own students. The rest of them I'm trying to be nice to. Okay. Right, so this is our very first example of a very typical situation in discrete differential geometries. We have different discrete objects with the same convergence. Yeah? In fact, sometimes you have different discrete objects and some of them don't converge, but that's a point we'll try to avoid. Okay, any questions about our story so far? I think this basically completes the picture for 2D curves. I don't think there's a damn thing else we could do in the 2D case. Yes?
Are there other notions of curvature that we could use besides theta?
That's a fantastic question. Are there other ones? So we have theta, we have sine theta. Can we think of other functions whose Taylor series agrees with theta at 0? Tangent is one. And indeed, at the end of lecture today, we'll see that that leads to a third curvature, which is tangent of theta, and also makes sense for a different starting point. Yeah. Yeah, so it turns out there's a lot of geometry properties out there you might try to conserve, and sadly we can't have them all. This is a Tina Fey style argument. Okay, so now let's move from 2D to 3D. Obviously, curves in 3D are very complicated. Here's a pretty picture. This is irrelevant to this class. I just they were pretty. Let's see. And basically, the only thing that we did with 3D curves in our previous lecture, and it was something that made you guys uncomfortable because you're holding me to account this year, which is great, is we derived this Frenet frame, right, which is this moving set of 3 vectors, which is perfectly well defined, except in one really, really important case, which is a straight line. and in particular, for a straight line, straight lines do have well-defined tangents, for sure. It's just the direction of the line. But they don't have well-defined normals and binormals, right? Like, it can kind of be arbitrary. And that's really a problem from application perspective, right? Like, you don't want degrees of freedom like that, because then it's kind of meaningless what you're doing. You're just guessing, yeah? That said, there have been, so we're going to talk about some alternatives to Frenet frame in a minute, which are kind of cool. One thing that's worth noting before we do that is that there are many attempts to discretize curvature in Frenet frames, and they actually show up. So for example, in nuclear magnetic resonance calculation, people do these kinds of things on these purely discrete objects that are like chains of molecules. You really want to measure some discrete notion of curvature there, because there is no curve sitting underneath these things. And so there were some really interesting derivations of useful formulas for these things. In fact, it's funny, because while I was teaching this class, this is a very typical way to teach intro to discrete differential geometry, to start with curves, and then quietly we all teach Frenet frame, and then we just kind of omit it when we do the discrete case, and talk about this other thing we'll mention in a second. And I spent quite a bit of time preparing this course, like looking for discretizations of Frenet frame, and they're few and far between. Like, people don't use it a whole lot. But there is this one, which I encourage you to read, this little discrete math paper from 2006, because it actually does have a pretty reasonable discretization of Frenet. So in particular, here's the way that they reason through it. I don't think there's a whole lot of preserved structure here, but it is kind of a reasonable way to make one of these objects. And essentially the starting point, which I think is very like typical reasoning in this field, is you say, like, what are the easy things we can define and we all kind of agree should be what they are. And then we'll go from the easy ones to the harder ones, and the more information that we collect, maybe the easier it gets. So in particular, in this work, which I believe is actually pretty close to almost all of the discretization of Frenet frame I was able to find. So again, we have this polyline like that. Now it's in 3D, which is a little frustrating because I can't draw it here, but we'll make do. So what is, among the different elements of the Frenet frame, we have tangent, the normal, and the binormal. Which is the one that's probably the easiest for us to discretize? If you guys are all engineers, mathematicians, what do we think? The tangent, right? Like somehow we all agree on what the tangent is. Well, I think, let's see. So what do we think, how should we discretize the tangent? Yeah.
Following the line.
Following the lines, right? We got lines, it's like the only thing here that we got, we all agree. So maybe we stick a tangent along each of the edges. We say like, okay, the tangent I'm just gonna think of as like, take the edge and divide it by its length. So it's just like some unit vector in each of these directions, okay? So there's like T1, T2, T3, okay? Good so far? Cool. So that much we all agree on, right? Like, so that's our first formula here. And what these folks do is kind of clever. They say like, okay, I think when we do this in mathematics, we usually define the tangent and then the normal and the binormal, right? Because that somehow makes sense from a calculus perspective. And the problem is we don't have calculus anymore. We have this discrete object. And they say, well, a different thing we could do is actually think about the binormal first. Because actually, to go back to our question from early in lecture, remember we had that really mysterious picture with these three axes and these little turning angles? How do we interpret maybe the binormal? Well, it's sort of like the normal to the plane in which the curve is rotating. Does that make sense? Well, in that case, a kind of reasonable definition of binormal, when you say like, okay, so about this vertex, like roughly what is the plane where this curve lives? Well, actually that's a well-defined object. It's just sort of the span of these two vectors. So if that's my reasoning, then what should I call the binormal? Say it louder, you got it. Even louder.
Cross product.
Thank you, the cross product of these two guys, right? So now I have the binormal, which I'm going to purposefully draw as something that's not perpendicular because it's actually coming out of the board, right? And this is the binormal, like B1. And now we're cooking with gas, right? We have a tangent, we got a binormal. What am I going to do to get the normal? I'll give you a hint, it's the same answer as the last one. Cross product. That's right. Now, there's an issue. Which hand do I want? How about on the back? You haven't. Non-normalized. That's actually not true because if tangent is a unit vector, the cross product of oh, I'm sorry. No, you're right. Yeah, this you should normalize B. That's right. So I'm being an idiot. Yeah, so you might want to divide this thing by its length. So first of all, if this thing is 0, that's going to be an issue. But let's assume that it's not. What's going to be another problem? Yes, Anna.
Some things are vertex quantities and some things are trace.
That's right. So I kind of want my normal to maybe, if you work through your right-hand rule, like you look at that picture, it should be the cross product of binormal and tangent. There's a problem, which is the binormals live on the vertices, the tangents live on the edges. So what are we to do? Well, what this paper does is says, you know, maybe my curve is sampled well enough, I'm just going to grab the binormal from a vertex and a tangent from its outgoing edge and call that the discrete normal. That's perfectly fine. But this is essentially where this theory breaks down. It's kind of funny. You have a well-defined tangent and binormal and not a particularly well-defined normal. You know? A different thing you could do might be to average adjacent ones or something like that. But then to go back to our comment before, you'd be more likely to get a 0 than you know, be very careful about dividing by zeros. So anyway, this was sort of an early attempt to make Frenet frames work. And I think there are a few things to take away from this. One is that actually the two things that seem to be pretty unambiguous to define are actually the tangent and the binormal. We'll see that that's true in the next paper we talk about as well, which is kind of surprising because it's not the way we think about smooth curves. The other is that Frenet frames are really annoying to work with. Like even in this attempt here, as we said, if I really wanted my binormal to be unit length, I should divide this number by its norm. And that's a problem because in a straight line, right, we have two adjacent tangents that are the same. I have no binormal. Yeah, so this thing is kind of like the curvature weighted binormal. In fact, we'll see in a minute. It's exactly that. Okay? Anyway, there are interesting things people do with this. So for instance, we have those Frenet-Serre formulas that tell us how the tangent normal and binormal kind of move along a curve. This paper actually does something similar in a different one in 2011. Physical. Notice, interestingly, these things tend to be published in physics. They don't tend to be published in like computer graphics. It's a different community. Which sort of says, well, a reasonable thing I could do would be to derive a matrix that tells me, like, if I have this oriented frame at this vertex, how to make it into the one there. This is a computable thing, right? And that thing is going to be kind of like the placeholder for Ferney's array that we had before, and they call that transfer matrix and show that has to do with, like, interesting quantities along the shape. Yeah. So anyway, I only include this stuff not to necessarily highlight this as like the exciting application of discrete curves as much as just like, hey, there aren't that many attempts out there to discretize the Ferney formulas. This is one of them. And B, it's really subtle how to do it because like we've pointed out, if you do the most natural choices, you do really, really well, and then you try to define that last thing and it ends up in the wrong place, right? Like some numbers are on vertices, some are on edges, and that's a problem because then they can't talk to each other. They live in different parts of our space. And that's where the engineering starts to happen, yeah? Sadly, this is the case almost everywhere. I mean, in my research, like there are so many examples where like, another good one is solving advection equation on meshes. If you do fluid simulation, you'll end up in this situation a lot where like velocities are on edges and densities are on vertices, and at the end of the day, like I need to move my gas along a velocity, but it doesn't exist where I need it, and so these are very typical things we have to cope with in this domain. Isn't this fun? Like essentially all we've done is like the 1D really stupid case of this stuff, and already like every theme that comes up this entire course is just like staring you in the face. But right, like so the larger issue with the Ferney frame is that it's mildly useless, and the reason is that it's very easy to introduce zeros. Like if there's zero curvature, then suddenly the normal and binormal are not necessarily well defined. Similarly for torsion and some other stuff. And so what are we to do? Well, it turns out in a lot of applications of discrete curves, we just use a different frame. We don't use the Ferney frame, we use some other interesting ones instead. And so for the rest of today's class, I thought I'd motivate one interesting choice, which is a popular one in computer graphics domain, was proposed, gosh, 2008. Oh boy, you guys were like not born yet. But it's essentially is used for one really interesting application of curves, which many of you may have kind of encountered if you dig through graphics papers, because it's a popular one. And this is in simulation of elastic rods. So here's the broad picture. I'm trying to simulate my shoelace, or I don't know, this cable sitting in front of me, or whatever. Right? And somehow these feel like one-dimensional objects, right? And so I feel like I should be able to simulate them as curves. And that would be nice, right? Somehow then I'm reducing the degrees of freedom. This is a physics problem. There's some really fun stuff to be done. But there's a lot of subtleties when it comes to simulating these objects and even representing them computationally. And that's sort of what this paper tackles, and what you too will tackle on your homework, because you're going to implement it. Okay, so in this paper, we're trying to capture interesting phenomena like what you see on the board here. So here, I've taken, or my virtual person has taken a piece of string, and they've held one edge fixed, and they've just twisted the other one more and more and more. Okay? And as you do that, I encourage you to all pull out your shoelaces right now and give this a try. Nobody ever does. These like weird shapes start to form. There's like little twisted over objects, like this thing in the top is sort of the classic one. Anybody know what this is called, by the way? Apparently this is called a plectoneme. Fun physics fact. So here's what this looks like in simulation. We're simulating our curve. You can see the virtual twisting happening on the right. Eventually these things turn into this knotted up mess, and it forms this little like helix shape in the middle. And this is expected behavior. In fact, there are physicists out there that have studied exactly this phenomenon and ask questions about like, the coefficient of restitution of the elastic rod relative to like how many twists are in this object. Those kinds of questions are interesting ones to study, right? In other words, like how many times do I have to turn the thing on the right for this to buckle, right? So those are the kind of simulations we like to carry out. Now the first question I should ask is a discrete curve, as we've described it so far, so just like a sequence of points, is that going to be sufficient for this simulation? What do we think? I see a lot of head shakes. And I never know if the head shakes are just because when I ask a question like that, the answer is no, or if we actually know what's missing. Like, what's missing in the simulation? What can I capture?
This sort of element of torsion between two discrete.
That's right. We have no notion of twist, right? Like holding a straight line curve and a straight line curve where I've twisted the end, both have the same sequence of points along this thing, right? So we need one additional degree of freedom here, which is like the spinniness of my curve as I move along this thing. Okay? So in order to do that, we're going to work in a really interesting physical universe, which is the space of adapted framed curves. Okay? So here's what this is going to look like. We're going to have, so notice that once again, the one thing that is well defined for this piece of geometry is a tangent. That is the one thing we can always agree on. Yeah? But now, notice that they've rendered it kind of cleverly with this little like candy texture here. And this is to give you some indication of the orientation of the curve. And the way to think about that mathematically is that we're going to make a different frame. We're going to have two different frames along our curve. Neither one of them is the Frenet frame. But now we have a new one called the material frame. And this is describing like the twist of the material from a flat position. Okay? Now we're going to see this a little bit subtle how we actually define this thing in a minute. But for now, bear with me. To every point along this material, I'm going to assign three vectors, t, which is the tangent, and then m1 and m2, which is like the orientation of the curve locally, right? Like the twisted thing. Make sense? Cool. So we're trying to do physics, which means that we need like energies, right? We need to know like what's actually determining the dynamics here, yeah? And these curves, these objects, elastic rods, it turns out they're principally governed by two forces. One of them, as I twist, is that it wants to untwist, right? And the other one is that if I stretch it, it wants to unstretch, right? And those are somehow two fundamentally different things we have to worry about. Does that make sense? Oh, and beyond stretching and twisting, even if it's inextensible to the third one, sorry, which is bendiness, right? Like the curve kind of wants to be a straight line. Maybe it's like a rod. And as I add curvature, maybe it wants to undo that. Does that make sense? Okay. So we need energies to measure these things. Because once we have energies, we can do Newton's laws, right? And so in order to measure those, the first one maybe is that bending energy. So like how different are we from a straight line? And the standard way to measure that would be to take the integral of curvature along your curve squared, right? Notice that when I'm on a straight line, the curvature is what?
0.
Thank you. And the bending energy is hence also 0. That's right. And as I bend this thing more and more, this kappa quantity increases, and this energy gets even larger. Remember that Newton's laws are, trying to reach some equilibrium. Okay. There's a problem, which is that we're used to measuring energy as derivative of tangent, and we wrote all those Frenet array formulas, but we don't have those anymore because we don't have a normal and a binormal. We just have a tangent, right? So on the screen here, we figured out how to cope with this. This looks very much like our derivation of the Frenet frame in the previous lecture. In particular, what do we know? We know that the curvature-weighted normal is the tangent differentiated, yeah? And now I'm going to take this guy, and I'm not going to write it in the T and B basis like we did in our last lecture. I'm going to write it in the T, M1, M2 basis like we have now, right? So this formula is exactly our proposition from before for orthonormal stuff. With me so far? I can write it on the board, but like this is pretty simple, I think. Okay? So there's three terms here. If you remember our proposition, I claim that this first value is 0. Why is that? Somebody new.
Norm 1, right?
Yeah, so t is a unit vector. And remember, we showed in our previous lecture that if I take the derivative of a unit vector, I get that it is orthogonal to the vector itself. So this dot product is 0, meaning what? Meaning that the curvature is essentially in the M1, M2 frame, like this, right? And here's what we're going to do. It's a total cop-out. We're just going to define two numbers called omega and omega 1 and omega 2. Those are going to be our placeholders. So rather than curvature, we're going to manipulate these two values here. So if I want to compute the bending energy, I'm just going to call it this thing here, and we're going to talk about how to compute it in a minute. Okay? Notice that this is exactly the same as the integral we had before. It's just in a different basis. Everyone with me so far? Like this is a reasonable number? Notice so far this has not involved the twist, right? This is, even though it's involving this twisting frame, because it's equivalent to this formula here, it really isn't sensitive to the twist. Okay. The next thing we want is to measure the twist, right? Like in other words, if the curve is all knotted up, it wants to unknot itself, right? And we can do that as follows. So in particular, we can look at the rate of change of M1 and M2, right? Now, we've got this, remember our kind of picture. We've got this curve. I'm sorry, I'm making a rude gesture at all of you. You have the unit tangent, and then you have this material frame, like these two other vectors, and they're kind of twisting like that, right? And the twist intuitively has to do with the change of the material frame, right? Because even if I'm moving along a straight line, it's rotating about this thing. Does that make sense? Well, I have M1 and M2. It's sort of enough to just consider the change in like M1, because obviously the change in M2 is the same. They're just 90 degrees from each other. And so in particular, the derivative of M1 has two components. One of them is parallel to the tangent. One of them is parallel to M2. Does that make sense? Remember, we have one theory, and we're just going to keep applying it over and over again. M1 is a unit vector, which means in particular, M1 is perpendicular to M1 prime, right? Nods? Agreement? Yes, I'm with you, and I'm very excited about elastic rods. I would like to do this on my homework, which I will do tonight. Good, good, good. Right, so this quantity M1 prime, which is what encodes the twist, has two pieces, right? One in the M2 direction, and the other one, which is in the tangent direction. If you think about it, the change in twist in the tangent direction is just kind of due to the curvature of the curve, right? Because it's kind of just measuring like the curve bending about itself. So the remaining piece is just M1 prime dot M2. One thing you might double check is just that that's the same thing as M2 prime dot M1, which it is up to sign. And that's okay, because we're going to square it and integrate it. So at the end of the day, our twisting energy is just going to be this quantity squared and integrated along the curve. One thing you can check here is, for instance, if my material frame is constant, like I have a straight line and the frame is not changing, what is this quantity? If I have an untwisted curve and I compute its twisting energy, thank you. Okay.
Do you want that to be a time derivative or an S derivative?
An S derivative.
Yeah, that makes more sense.
Yeah. Oh yeah, so here, yeah, I guess everything is in S, so that's why primes and dots, if that's what you're used to, are kind of the same. Yeah. Okay, so there's only one problem, is we need a way to store this M1, M2 thing along a discrete curve. We haven't talked about that. Like, what does that even mean, right? And remember our sort of philosophy in differential geometry a lot is we want to store everything relative to a canonical frame. And so far, the only choice of canonical frame we have is this Frenet frame. Right, so you can imagine a universe where I store M1 and M2 as like kind of a rotation of N and B. But that's not so great because N and B don't make any sense when I have a straight line. And so how do we get around this? We just use a different kind of framed curve instead, which is kind of connected to this particular application. And that is a different object called the Bishop frame. This is sort of like the hipster frame curve. And so this is essentially a different way to compute a moving frame along a curved object. Now, the Bishop frame and the Frenet frame are just two completely distinct objects. But they agree on one thing, because we all agree on one thing about a curve, and that's that it has an unambiguous tangent vector. Okay? But essentially, the normal and the binormal change to some other pair of vectors. And the way that the Bishop frame is determined, we're going to skip a little bit of the math, but I'll let you check it at home. Which is, by the way, whenever your professor says that, it's because they forgot how to derive. But in any event, there's a problem, which is if I have a frame curve which is like twisted about itself, that's not particularly canonical to the curve. That's telling me about the physics, right? Like there's more, it's describing a curve and its twist all at one time. If I want to just describe a curve, then that frame doesn't make any sense. And so, but I'm working on twisting related problems. So somehow I want like a twisting related frame. So one thing that I could do would be as follows. I'm going to fix a frame at one point along the curve, like maybe just at the very beginning of my curve, I just choose a frame to like align to M1, M2, whatever. Now I'm going to take this twisting energy, I'm going to optimize it. I'm going to find the set of frames, like the M1 and M2, along all the rest of the curve that makes for the minimum amount of twist. Right? Like for instance, I could choose a frame that like spins around the curve all like wild and crazy, but that'd be a pretty weird choice of canonical frame. So instead, the Bishop frame is the one which is chosen to have the smallest amount of twist as I move along this thing. So there is one degree of freedom. Like I have to choose the frame at one point. That's going to be kind of okay here. But then once I do that, the way I'm going to get the frame everywhere else is by minimizing twist. It's like sort of the least amount of work that I need to make a new frame at a new point. Yes?
Confused what you're talking about. Why can't you store the tangent and the two m to any basis?
You can, but it would be useful to have a basis where your computations are really tidy and that are sort of intrinsic to your geometry. You're right, you could store them in XYZ if you really wanted to. But that's going to turn out to make for very ugly formulas for these energies we wrote down.
Okay.
Yeah. Okay, so it turns out, and here's the part that we're not going to do today. I believe you could derive it using that first variation. Like, so once you've become experts on first variation formula on your first homework, if you want a challenge, you can derive this thing by optimizing that twisting energy. What you can show is that there's a fourth vector, which is called omega. And you can obtain the entire, what's it called? Oh, sorry, words are failing me right now. You can obtain the Bishop frame by solving an ODE, where there's some function omega. This is the curvature-weighted binormal. Notice that this object is exactly the same as the one that we had earlier when we were computing Fourier frames on discrete curves. And if I solve this ODE up here, namely t prime is equal to omega cross t, and now u and v are going to be my, my Bishop frame rather than like before we had n and b, right? Then they satisfy this funny relationship that like the derivative along the curve is the cross product between t, u, and v in this very carefully chosen object here. This is a messy formula to derive, but we can thank Bishop for it. If we had more than one lecture on this topic, we would derive it on the board. Okay? But the intuition here is quite simple, is that this Bishop frame is the one where I choose it at one point. Like I choose t, u, and v right at the end here. And then this gives me, this ODE gives me a way to find it everywhere else. Does that make sense? Okay. So, right, and incidentally, you can show in this thing, unsurprisingly, that this satisfies this no twist condition, namely that u prime dot v is equal to 0. In fact, that's one way to derive this set of equations here. Obviously, if you can find a frame for which this is true, then notice that that necessarily is the minimum twist frame, because what is the twisting energy? 0, right? Cool. All right, so that's all we're going to need to discretize the system. Yes?
So, like in terms of numerics, I can't see a good reason to do this. Is the reason you do this so you can do perturbation theory in analytics?
So why don't we do the numerics, and then we'll come back to your question.
Okay.
Yeah. So let's do exactly that. Why does this give us a nice way to represent a discrete curve? Okay. So first of all, remember we want to represent a curve undergoing this particular physical system, right? And what we're going to do is choose degrees of freedom for our system that are going to make the ODE or the PDE that we have to solve a lot simpler, right? That's sort of our goal here, is to make like something that's easy to discretize in space and time. And it turns out that this particular choice of basis is going to do that. So what can we do? Well, now that we have this canonical frame at every point, we can describe the material frame as a deviation from that, right? So at every point, I can think of the M1, M2 as just a rotation of u and v about the tangent to the curve. Does that make sense? Yeah? Okay, cool. So in other words, there's now a theta at every point along my curve, which is giving me the kind of twist of the material frame. Notice that like we're only going to care about derivatives of theta, which is why it's sort of going to be okay to choose the frame at one location. Okay, so now if you go back to the twisting energy formula, you'll see that it's nothing more than the derivative of theta prime, which kind of makes sense, right? This is kind of like, you know, if like I'm a candy maker and I'm like manufacturing that like little swirly candy cane texture that you saw before, right? That's like the amount that I have to like twist it as I drive along the curve to get that texture, right? That's really what's going on here. Okay. So if I want to simulate my curve, right, this elastic curve that's bending and twisting over time, I have basically two sets of degrees of freedom. One is the shape of the curve, which we're going to represent just as a polyline. And the second is an angle, the twist angle of this object. But it's a very, like, even deriving, like, what does this angle theta mean is a little bit tricky. It is the angle that your curve, as an oriented object, is distinguished from just the most relaxed possible configuration. And it turns out the physics in these particular coordinates is very clean. To go back to your question, by the way, what else could I do? Well, I could have the material frame be just two vectors, but now I'm going to have to add constraints that they're normal, that they're orthonormal to one another, right? Whereas here, I'm just down to a scalar at every point. Okay, so let's discretize this object. I'm going to follow the notation in this research paper because part of your homework is to read it. And unfortunately, it's going to clash a bit with the notation from last Thursday. So just, you are aware. Everybody take deep breaths. It's about to happen in like 3, 2, 1, right here. So we have upper indices and lower indices, and we're not going to couple them together in sum. Okay? This is the one time in this course where this happens. I promise. So don't imprint too much. Okay, so in this particular research paper, the notation is that lower index means it lives on a vertex, and upper index means it lives on an edge. So it's also a reasonable choice, although I kind of wish they'd chosen something else because it like looks like differential geometry, but it's not. Okay, so in particular, we're going to say that the x lower I are just the vertices of our curve. That's the one thing we can all agree on, right? And we have these edge vectors, which are just differences in x's. So notice that by virtue of subtracting the x's, we now have an upper index. Yeah? Everybody with me with my notation so far? So as always, in our oriented material frame, what is the easy thing to compute? The tangent, right? So what is the tangent? It's just e divided by its length. Yeah? There it is. Okay. This is like the one kind of unambiguous thing that we usually, I would struggle to think of a discretization of calculus on curves that doesn't do this. Okay. So now it's going to turn out that the convenient way to measure curvature, if you kind of go back through that variational picture, but you do it on this particular object, you're going to end up with a 2 tangent of the turning angle divided by 2. Here it's a phi, it used to be theta. That's just because we're using the notation in this particular research paper. And in particular, the reason for that is going to come from this formula for the curvature binormal, which is actually the same as the Frenet frame paper we talked about before. So remember that we can get binormals by taking cross products of kind of adjacent edge tangent vectors. So if you do that, you can just kind of define that thing to be curvature binormal. It turns out you need to normalize it a little bit to account for edge lengths. And if you sort of work through that formula and then just do lots and lots of like high school geometry, you'll show that this like complicated object, when you take its norm, just ends up being this formula on the left-hand side. This is the kind of manipulation we do a lot in this class, is like take derivative of something in coordinates, get an ugly formula like the one on the right, and then do lots and lots of high school geometry until we convince ourselves that ugly formula is actually equivalent to something clean. Such is life. Okay, so now we can start to discretize different numbers that we had before. One of them is the bending energy. So remember, we have this curvature binormal now on every vertex. And remember, what is the bending energy? It is the integral of curvature squared, right? And here's kind of a subtlety. We don't have curvature squared. We have curvature. In fact, we have curvature integrated over these segments, just like before, right? So if I take the norm of this discrete curvature binormal, it's actually integrated over that dual cell. And this is going to become a problem, because if I take the norm of this thing, I get some value that looks like the integral of curvature, but I need the integral of curvature squared. So in order to do that, this is where there's a bit of an interface between discretization and discrete. It's actually not clear that there is a discrete formula from these curvature binormals, so we have to make a bit of a conceit here and do a best approximation. So you take that binormal, you divide it by the length of the cell. Well, now this is kind of a pointwise quantity, so I can square it. To integrate it, I multiply it again by the length of the cell. Notice that there's like somehow not very much preserved structure here, but it's sort of the best we can do. And it turns out qualitatively this energy seems to behave well. But if you're looking for like a little hole to punch in the physics, this is where I would do it. The other thing that you need is a way to compute that material frame so that you can simulate twist, right? Because that's what you're going to need for the twisting energy. In order to do that, remember that the material frame is this thing that's somehow the most relaxed, twist-free frame. And so I'll let you look at the details in the research paper, but there's sort of a clever discretization. They say, okay, one way to view that is to go back to that Darboux formula, where you have that cross product with omega that's kind of telling you how the material frame changes along the curve, right? And one thing you can do is say, okay, I'm going to think of there being like a little matrix that sits on every vertex that's going to take me on the frame sitting on one edge to the frame sitting on the next one. And what do we know about that matrix? Well, for one, it had better take the tangent to this guy to the tangent of the next guy, right? So P times the previous tangent equals the next tangent, right? And then eventually we're going to say that when I apply P to like the previous U, I get the next U, and similarly for V, yeah? And everything you can do is say, aha, well, in the most relaxed possible frame, there's never a time when I should twist. So in particular, in the sort of binormal direction, I should leave things alone. And these two facts on the top are enough to determine an orthogonal matrix P. This is our first appearance of a notion called parallel transport. And given this thing, now I can compute a material frame along my entire curve, where what I do is I have a frame on one edge, then I can kind of compute the P associated with the vertex, that gives me the frame on the next one, and I kind of keep chaining my way along the discrete object that way. Okay? Whew. So once I do that, now I can talk about a twisted material, which is going to be one number per vertex, right? Which is going to be that theta, which is describing this sort of twist that happens. So in other words, like I have some oriented frame curve here. I could do parallel transport, like I could do the most relaxed possible way to get the next frame here. And then I kind of think of twisting after that, right? And that amount of twist is going to be the theta I that's sitting at this vertex, okay? So anyway, this is just to give you a coarse idea of how people go about discretizing these formulas. Notice that it's really tricky, and that essentially getting all these things right involves placing different things on vertices and edges in very careful fashion, making sure they agree with some divided difference formula maybe, and so on. So finally, then you have a discrete twisting energy, and now we've done all this work to essentially lead to a very clean simulation energy, because at the end of the day, we have all these thetas, and what do we know? We know that the twisting energy is kind of like the integral of the change in the twisting angle squared, and now that has just been exposed to us, so the twisting energy is quite easy, okay? So in any event, I'm rushing through this a little bit because as usual, I'm bad at time management. You guys should read this paper to get some more details, but essentially this is the high level idea, is you've got all these quantities of interest. The first thing you have to do is to define degrees of freedom that make sense for your problem. And then after that, unfortunately then, like the energies don't turn out to make sense. You do have to end up doing some approximation. It's very tough to make this whole universe kind of work out in one shot. Okay, so we're going to omit the physics, and similarly in your research, your homework, you won't have to do it either, but we've covered the whole geometry part of this paper. If you want a fun read, there's an extension of this paper, we mentioned it in a previous lecture, which simulates not just pieces of string, but also like things of honey coming out of like a tight nozzle. So now there's a little bit of fluid dynamics here too. So I encourage you to give that paper a read. It's a fun project for this course if you like physics. And they claim that they're the first fluid mechanical sewing machine, which apparently is what you call this little experiment. So to conclude today's lecture, the high-level point here, we went through 3 different research papers. One which is deriving curvature as a turning angle. One is deriving curvature as first variation of arc length. One that's doing it based on a physical problem that people want to solve. And they led to 3 completely different notions of the same number. And that is life of the city in this discipline. You have different preserved structures that you want to have, and unfortunately, all of them lead you down to different objects in the discrete case. That's sort of the big theme in this field. Moreover, just another takeaway is that the central object of study in smooth differential geometry ends up being a little useless in applications, so you have to define something else. Okay? And that you need the right degree of freedom. So, with that, in our next lecture, we'll do what probably most of you guys think of as the core topic in this course, which is to talk about surfaces. So we'll first tell you how to define a surface, and then how to do all the analogous computations of what we just did in 1 dimension higher. So with that, have a lovely weekend. Remember, I will not see you on Tuesday. I won't be here, but I will see you Thursday. Okay.